All right, moving on to problem number 4. So problem number 4 here, determine the pH of a solution of 0.100 molar benzoic acid, and then we're given the Ka of benzoic acid. So given the name, it should be fairly easy to identify that benzoic acid is a weak acid. And that means we have this type of equation. I'm just going to use HA for benzoic acid. The actual formula of benzoic acid is irrelevant to the problem, right? Unless you're going to have to go back in and figure out how much to weigh out to make a certain solution where you need the molar mass. So all we really need to know here is that it's a weak acid. Weak acid, benzoic acid, would react with water, which of course is a pure liquid. That would establish an equilibrium. Acids donate H plus in aqueous solution, so the acid will partially protonate the water, which would give us hydronium ion in solution, right? And that would leave the conjugate base of the weak acid, which would be A minus, right? Which would be benzoate, but again, that name is not really relevant to our problem, right? That will be our equilibrium. Now, with that reaction, we can think about an ice chart, and we also can think about what's the equilibrium constant expression. That is what we'll use the ice chart to develop a calculation that can get us to the information we're looking for here in the problem. Now, initially, all we have is our unreacted concentration of acid. So the concentration here is 0.100 molar. Water, being a pure liquid, would not appear in our equilibrium constant expression, so we don't have to worry about the molarity or the concentration of the water. Under initial conditions, we don't have any product, so both of these would start out as 0 in this case. Zeros, super helpful here in an equilibrium because the zeros tell us which way the system's going to have to shift to arrive at equilibrium. We can't have any zeros when we get to equilibrium, so these zeros will have to go away. That means the reaction is going to shift forward. It's going to make some of that product, and we're going to lose some of the HA. That's how we'll get the pluses and minuses that go along with our X's. So if we lose X amount of HA in terms of molarity, this is a 1-to-1-to-1 reaction. We're going to get X in terms of change in molarity for each of the products. At equilibrium, this would be 0.1 minus X. Now, it is a 3 significant figure concentration, but for simplicity, I'm going to leave off those trailing zeros for the moment, but we don't want to forget that when we get to the end. 0 plus X would be X in each of these cases. Now, that's our ice chart. We know how to write an equilibrium constant expression, hopefully at this point. So based on this reaction, products go on top. That's the hydronium ion concentration and the concentration of the conjugate base of the weak acid. On the reactant side, we just worry about the concentration of the weak acid. Again, the pure liquid, water in this case, will not appear in the equilibrium constant expression. Now, we've got Ka, we've got values for all of the concentrations. We want to think about plugging this in. Now, in this case, though, there's a approximation we've talked about that will allow us to determine, do we need to worry about that minus X? We just plug this in, these as X, this is 0.1 minus X, and this as a number. This will work into the quadratic formula, and we'll get an X squared term and an X term and a numerical term. Set them all equal to 0. We can use the quadratic equation to solve for X. Most of the time with weak acids and weak bases, the equilibrium constants are low enough relative to the concentration that we can ignore how much of the weak acid dissociates or reacts in this particular case. So we want to look and see if that's something we can do for this particular problem. Now, what I've suggested in the videos is a technique that's a little different from what is described in the book. So hopefully you've been paying attention. What we want to do is we want to compare the concentration of the weak acid to its equilibrium constant. If the equilibrium constant is really low compared to the concentration, then the reaction doesn't move forward much. So that's a good way to evaluate their differences. So if I take the concentration of the weak acid, so let me just write this over here, assumption. if I take the concentration of the weak acid in this case and divide it by Ka, that's 0.1 divided by 6.3 times 10 to the minus fifth. What I've said is if that is 1,000 or more, then this is a reasonable assumption to ignore that x in the bottom of our equilibrium constant expression. Now this one comes out to be 1,587, and there's some change there too in the decimals. So this is, benzoic acid is actually one of the stronger weak acids with a 10 to the minus 5 constant. But at this concentration, that is still a good assumption to just ignore the minus x term here. So if we can leave that out, that makes this a much simpler problem. Now all we have to do is plug in, solve for hydronium. Now I didn't mention this yet, but pH, that of course is linked to hydronium ion concentration. Hopefully you know that relationship, although we'll get to it here in the problem if you're not quite sure. So let's plug in here and then solve, see if we can solve for x. We've got Ka for benzoic acid provided in the problem, so 6.3 times 10 to the minus fifth. We called both of the products, hydronium ion and the conjugate base, x, so that'll be x for each of those on top there, x squared. And on the bottom, since we were able to eliminate that negative x, that's just going to be 0.1. So we can solve this equation for x in a pretty straightforward fashion. If I take the 6.3 times 10 to the minus fifth, multiply both sides of the equation by 0.1, so times 0.1, that would give me 6.3 times 10 to the minus sixth equals x squared. Take the square root of each side, and that's x. So I'm just going to take the square root of that answer, and that'll be x. So x is 2.51 times 10 to the minus third, right? And that's concentration, so that's a molarity. Now, back in our ice chart, that's what we called the hydronium ion concentration, right? In addition to the concentration of the conjugate base. But hydronium ion concentration, again, is what relates more closely to pH. So if the hydronium ion concentration is 2.5 times 10 to the minus third, and the way we define pH is that it's the negative log of the hydronium ion concentration, all we need to do is take the negative log of our answer there for what was the value of x, and that will be the pH. So that's in my calculator. In this calculator, I can take that value and I can just hit the log button. So log log, so base 10 log, right? And then change the sign, and my pH is 2.60. Now, in fact, in this case, we had 3 significant figures here in our concentration, and that means we can have 3 significant figures past the decimal. So we could add that next 0 here in this case as well. Nope, I went too far. It's really only 2 significant figures back here for K. So we have 2 significant figures really in this answer, so don't add that extra 0. Just 2.60 for our pH value for this weak acid. Okay, all right, we'll stop there for number 4. Pretty straightforward weak acid question there. You certainly should be ready to tackle a problem like this, and also to evaluate this assumption, because again, if you can't use the assumption, then you've got to go through the quadratic formula, which will change up the problem a little bit differently. But if that's the case, that this is less than 1,000, this ratio, then taking out that minus x will actually give you a much different answer, right? In this case, because that ratio is so big, the answer you'd get if you used the quadratic equation would be very close to 2.60. So not a lot of change by removing the x. So be aware of how to do that, and look for this type of problem on that upcoming exam.